Hello everyone. This video is going to be another demonstration for energy conservation. Okay, so um, and this example is kind of it's energy conservation between kinetic energy and elastic potential energy. Okay, so let's see the description of the problem. It said there's a block, okay, with a mass 0.8 kilogram, and then its velocity is 1.2 meter per second, and then he collide with a stream, and then he collide with a stream, and initially this stream is unstretched. Okay, it's stretched there. That means there's no elastic potential energy of the spring beginning. And give it a spring constant, spring force constant K equals to 50 Newton per meter, and and he said try to and the problem want to ask try to find the maximum compression of the spring after the object hit after the object strike the spring. Okay, and it also says that this surface I think it should state more clearly. I think the surface behind the surface underneath the spring is has a friction. I mean, the kinetic friction coefficient is 0.5. So that means, okay, when when the object hit the spring and then compress the spring during this process, it also has the friction force drag this object. Okay, so I think probably the description of the problem. Okay, let's go into the calculation, and we are going to use the energy conservation to calculate this problem. Okay, to solve this problem, not calculate only. Okay, then let me switch to this. Okay, and then let me add some information on this problem. Yeah, what's the mass? Okay, 0.8 kilogram. Mass. Okay, the mass is 0.8 kilogram. And the velocity, I think it should be more specifically. I think the speed is when the object strike the spring, and at that moment, or before the striking, before that striking moment, the velocity is 1.2 meter per second, and the force constant of the spring K is equal to 50 Newton per meter. What else? Oh, yeah, the kinetic friction coefficient nu K is 0.5. Oh, I forgot. 0.5. Yeah, I have very short-term memory. Okay, 0.5. And okay, that's probably all the information. Any any information? Okay. Okay, so let's start. Okay, like I said, we use energy conservation to calculate this problem. So energy conservation. Okay, let me write down the. Okay, for this energy conservation, we need the information of initial state and final state, the potential energy, and the kinetic energy of the initial initial state, and the final start. If you are German, final start. Okay, that's what's the kinetic energy at initial state? Okay, of the system at the very beginning, just as the moment right before the striking. Okay, the velocity of this object is 1.2 meter per second. So at the initial state, the system has kinetic energy because it's from the object. Okay, 1 over 2 mv square, and it's 1 over 2 0.8 and times 1.2 square. Okay, and at the very beginning, just the moment before the strike, do we have any potential energy? No. Okay. Just like I said, we just focus on the moment, just right before the collision. Okay, and initially the problem said initially the spring is unstretched. Okay, so if your spring is unstretched, it's relaxed at its relaxed state. There is no elastic potential energy. So U spring is 1/2 Ka square. Okay, but now it's unstretched, so x is sorry, x is equal to 0, so it's 0. Okay, as for initial state, okay, so and what's the final state? Okay, okay, what's the kinetic energy of this system at the final state? Okay, because he want to find the maximum compression of the spring. So what's the maximum compression of the spring? What and at what condition the system will reach the maximum compression? That's and that instinct and that instinct, the object will full stop. Okay, just like this figure shows. Okay, because the object strike the spring, and the spring has a spring force to resist the strike, and also there is a frictional force. So then the object will gradually stop. It will gradually stop. Okay, and at the moment it stops, the velocity of this object will become 0. Okay, and at this moment you will have the maximum compression. Okay, at this moment, when the object strikes the spring and gradually slow down, and then the velocity becomes 0. At a 0 moment, the velocity 0 moment, you will have a maximum compression. You will have a maximum compression of the spring. Okay, so between A and C, okay, you could there's between the state A and C, there's no maximum compression. Okay, the maximum compression only happens when the velocity of velocity of mass is equal to 0. Okay, so that's just what this picture shows. What's this picture trying to demonstrate? Okay, so we understand that when it's reached the maximum compression, on the velocity of this object becomes 0. So velocity is 0. That means the kinetic energy is also 0. So here write down the 0. Okay. And now, well, of spring, do we have a elastic potential energy? Yes, we have, because at this moment, just like I said, it's reached the maximum compression. So you have your spring is compressed. Okay, so just 1/2 and K, let's say X max square. Okay, and K is 50. Okay, so we all have the information of initial and final state. And next thing is we need to know also the Q and W. Okay, so don't forget the energy conservation is delta K plus delta U equals to Q plus W external work done by external force. So we also need to know the information of Q and WEXT. So since this system, there is no external force on this system. So okay, so there's no work done by the external force, so it's 0. And the Q, I think in this problem we have friction. So the friction generate heat, and it generate heat from inside to outside. Okay, it's release the heat, so it will become negative. It release the heat is negative, and we have friction force and times the distance. Because friction, you only care about the distance. We'll try to calculate the friction, the work done by the friction. We only have consider its distance. Okay, how long the friction force? How long? Not how long. How much distance when when the friction happen? Yeah, sorry, my English. I think that sentence is difficult to understand. Okay, so like I said, let's just say at the very beginning, the problem should say the surface under the spring is a rough surface. So when the mass collide with the spring, and then it will encounter a friction force, keep dragging the object. Okay, and what's the friction? What's the friction force? And the friction force, we need a little. I just do it again. Okay, how to calculate the friction force? The friction force normally is proportional to your normal force. Yeah, change to blue, but why is still? Yeah, very strange. Why is still blue? Oh no, why is still red? Okay, so the frictional force normally is equal to the friction coefficient times your normal force. And in this system, what's your normal force? Okay, let's just see. The normal force is, okay, yeah, why it becomes very strange. Very strange. Why it then cannot change the color? Oh my god, Okay. Okay, this object, okay, here it has its weight, mg, also has normal force, okay, and it has the friction force point to this direction, the friction force. Okay, because there is no acceleration in the y direction, because in this problem we just assume it's doing the motion in the horizontal direction, in x direction. There is no acceleration on the y direction. So okay, we will have the sigma Fy equal to may, and there's no acceleration y direction, so it's 0. Okay, so the sigma Fy, the net force on y direction is 0, so that means normal force minus mg is equal to 0. So the normal force equal to mg. Okay, so in this regard, we have minus nu k times mg times d. Okay, and we have the value to put in. Yeah, we have value. Nu k is 0.5. Don't forget minus sign, minus 0.5 times m. What's the mass? 0.8 kilogram. And gravitational acceleration and the d. What is d? Okay, because initially this spring is unstretched, and then the mass hit the spring, and then he's doing the compression, and all the way along to the maximum compression. So the distance, also the friction also do the distance for the friction is also x max. Okay, the distance for the friction is also x max. So here we just put the x max here. Okay, and so we get all the information. Okay, next thing is to plug everything into the energy conservation equation. Delta K plus delta U equals to Q plus W. Yeah. I think I will zoom in a little bit. And here. Okay. Okay, so let's write down. Okay, delta K plus delta U, it means final state kinetic energy minus initial state kinetic energy plus final state potential energy. Initial state potential energy equals to Q plus W EXT. Okay, let's put everything into there. Okay, it's final state minus initial state. What's the final state of kinetic energy? 0. Initial state kinetic energy. Okay, 1/2, 0.8, 1.2 square. So it's 0 minus 1/2, 0.8, 1.2 square. And what's the potential energy difference between the final state and initial state? Final state 1/2 kx max square to k x max square. Okay, and minus 0. Okay, and equal to this one's q is here, minus 0.5 times 0.8 times 9.8 times x max. Okay, and Wext is 0, so it's good. So we will have reached this equation. Let's do a little algebra work. Let me see. Because k is equal to 50, right? K is equal to, this is 50. So the final equation is, let me check my cheat sheet. Okay, so the final equation is 25x max squared. Okay, and minus plus, yeah, this use calculator to calculate 0.8 times 0.8 times 0.5 times 0 and times 9.8. What's the value? 3.92. Okay, 3.92 x max. And let's see, it's plus, so it's a minus here, so it's minus, what's the value? 0.576 equal to 0. Okay, and then we will have a quadratic equation. So how to solve the quadratic equation? I believe all of you can know how to solve the quadratic equation. Okay, if you forget, let me show you. X max equal to 2 times 25 minus 3.92. And then k in square plus 4 times 25 times 0.576. Okay, and then we have two, sorry, this is plus minus. Okay, when we have two answers, but the negative is not reasonable. Two answers. What two answers? Yeah, the negative value is not reasonable, so we only keep the positive value. Okay, that means we keep this term. It's what's the 8.54. Okay, plus minus 8.54. Yeah, like I said, negative value is not reasonable, so we only keep the positive one. So it's what's value with this 4.62. Okay, so it's 0.0924, and the unit is meter. Yeah, don't forget the units, because we are using the MKS system. The MKS system is Newton meter and second. Newton meter second kilogram. Newton meter second kilogram. Under this system, your length, the unit of length is meter. Okay, so this is also a very typical calculation for the energy conservation. So in this problem, the kinetic energy of object can be transformed to elastic potential energy of the spring, and at the same time, the friction also dissipate the kinetic energy as well. Okay, so that's the it's not really difficult calculation, right? Because energy conservation, everything is scalar, so very easy calculation. Yeah, compared to Newton's second law, right? Newton's second law is a lot of vectors. Okay, so I just start the video here, and we'll see you in another video. Okay, bye bye. Woohoo.